Okay, I'm starting this next lecture just maybe a few hours after the previous one, but I'm calling it for the next day so you can more easily identify it from the other one. Okay, let me just check everything. Oh, okay. So I wasn't connected there. So just to start over again, this lecture will be a continuation of the previous one. I'm starting it a few hours after that, but I'm calling it by the date the next day so you can more easily identify it. Okay, so that's why. Hopefully this is coming through so you can more easily identify. Okay. So it's working fine. Okay, so let's continue where we were, what we were doing last time. So last time I introduced the trigonometric functions. I looked at an example here where you can, given the sides of a right angle triangle. If you're just given those sides, by the way, you should check to make sure Pythagoras' theorem is true. In this case it is. And then once you're given those side lengths, then you can construct all of the values of the trigonometric functions for the angle shown. The angle were over here instead, then you would get different values. The sine and the cosine would be interchanged. The tan and the cotangent would be interchanged, and also the cosecant and the secant would be interchanged. If you look at their definitions, that's how it would work. Okay, so I want to wrap up this chapter 7 that we've been doing, and also help you also in your use of the calculator a little bit more. So I did check out how to calculate things now, and so always check to see if the calculator is in degree mode or radian mode. In my case, I have a little symbol here which indicates radian mode. I don't know if you can see that, but it's right here. Yeah, you can see it where my finger is in front of. And in a second I will change that. That's in degrees right now. No, it is in radians right now. But you can do something like this. You can press mode, and then you go click this arrow 1, 2, 3 times, and then you have a choice of 1, 2, 3, and I'm choosing 2 for radians. And then it sets it to that value. It'll say D, R, or G. G is for grad, and that's a different unit system for angles, which we won't use. It's based on 100 rather than 90 for 1 quadrant. Okay, so here I will then do this calculation, which will now be easier than what it was last time. So I take this inverse sine of 0.6. Let's try that again. Inverse sine of 0.6. And right away it gives me the 0.6435 value, which was correct. I just did it in a longer way. And if you divide that by pi, shift pi, you get the value 0.205. So what that means is this is equal to 0.205. I rounded off that number times pi. So it's about 1/5 of pi. Approximately pi over 5. All right. Okay, so I would like to also do some exercises, but first I wanted to develop the theory a little bit more, possibly go into the next. I'll be covering a little bit of the next chapter as well by drawing the graphs here. But I think drawing the graphs now will help you to understand the sine and the cosine functions better. It's a lot better when you can picture them. And so let's go back to the unit circle approach. So we have the unit circle. I think this is running out. So we have the unit circle here. Now, we want to look at this function. Okay, we have the angle t, and we have the x coordinates and y coordinates, the x and y coordinate for the point that this ray intersects with the circle. So the unit circle is always x squared plus, it's the set of all points such that x squared plus y squared equals 1. So let's see what happens as we move this point along. And the question is, so really x, each of these values, x and y, each of the coordinates, it's a function of t. So what I want to show now is, this is a graph in the xy plane, so things here might be function, y is a function of x. In this case, the circle is not a function. It's not the graph of a function, because you can draw a straight line, a horizontal line, and it's not. It intersects the circle at 2 points most of the time. So it's not a function, but we're going to treat each coordinate as a function of the angle t. So that will be a function of time, or t. T, I'm a physicist, so I usually think of t as time. But, so we're thinking of this thing as moving in time, and as it moves, how does x change and how does y change? So we'll want to plot graphs of x as a function of time, and then y as a function of time. And that's how we defined the cosine. So this will actually be the cosine function, cosine of t. So notice I'm not putting brackets here. That's something you should do if you're using a calculator, because it might not recognize this. But for convenience, I just drop all the parentheses and the brackets for, so I write it like that, cosine of t. And later we'll draw the sine of t. Okay, so I want to draw enough points here that you can see the idea. So this is going to be pi over 2. This is pi. This is 3 pi over 2. And this is 2 pi. And then it continues, so I'll have to extend my graph, pardon me. It goes to 5 pi over 2, 3 pi, and then 7 pi over 2, and then 4 pi. So I'll draw two intervals, each of length 2 pi. And I'll also go in this direction so you can see what's happening here as well. So this is minus pi over 2, minus pi, minus 3 pi over 2, minus 2 pi. Okay, so what happens is first, so we have 1 here and minus 1 here. And then there's, you might consider the point halfway between, so plus a half and minus a half from the origin. Okay, so this is the t-axis, or the time axis, and this is the x-coordinate axis. So with this axis, physically what it's telling you is if you shine a light from way above, it will project this point and create a shadow on the x-axis, on this line. And this shadow will move along between this point 1 and minus 1. Right, this is a point on the x-axis. This is the x-coordinate on that, where the circle intersects the x-axis in the positive x-axis, and this is where it intersects along the negative part of the x-axis. Minus 1 and minus 1. So the point will go from plus 1 from t equals 0, and then it will start moving down through 0. This is where x will be 0, where it's the x-coordinate. There's no shift from the origin in the x direction when the point is right above the origin. So the shadow will hit this origin as this point moves through this point, which is 0, 1. And then as it keeps going, the shadow will move all the way to minus 1. So plotting that out as a graph, you start at 1 at t equals 0. Then at pi over 2, it goes down to 0, as I'm saying here. And then at pi, this angle here, this graph becomes minus 1. The y value becomes minus 1. So we're all the way down here. Then as I go through 3 pi over 2, the x-coordinate goes back to 0. So I go back up like this. And then as I go all the way around back to 2 pi, as t goes all the way around once, its value, as this line goes all the way around the circle, t goes all the way from 0 to 2 pi. So I go all the way up to here, because there, again, the coordinate, the x-coordinate is 1. So if I continue going around, the same pattern will repeat itself on the graph. So again, if I go to 5 pi over 2, that's just 2 pi more than 2 pi. Sorry, half pi more than 2 pi. And I go down. And then when I hit 3 pi, that will bring me all the way to this point. Again, the value for x will be 0 there. And then 0 again, and then 1. So if I draw this correctly, this should be exactly between 1 and minus 1, and it's probably not high enough, so I'll just draw a little bit higher here. Okay, so this is a graph on the positive, for positive t. For negative t, it will just go backwards, okay, starting from 1, and once I go down to 0, once I go, t goes this far in the negative direction, so minus pi over 2, then the value for x will again become 0 there. And when I go to t equals minus pi, the value of x will become minus 1. So I'll go up again. Okay, so this should be drawn smoothly, no abrupt changes, smooth curve. I'm sorry I haven't drawn it very well, but the book will have graphs of this, which will look a lot better. And so in it, you can see it repeats itself. So after a certain increase in the t variable, you're going to go from one position along the graph to another position somewhere, say here, which is basically a copy of this but shifted over. Okay, so this point, it's going to be on the right side, a little bit further down, just as it is over here. If you keep on going another spacing by the same amount, which is, you can see it's going to be 2 pi, you're going to arrive at the same position on the graph. So the shape of the graph is identical, it's just repeated and shifted over at the same time. Same thing down here. So the graph will, the equation for the graph will satisfy this identity. So if you add this p value, p will here be, say, 2 pi, then to the value of t first, and then you take the value of the function, which is the cosine in this case. Then you'll get the same as the value of the function before shifting it over by p. Okay, so this equation holds for all times t. all right, for a particular value of p. And if it does, if this holds, for a value p that's positive, then this function is said to be periodic. And now, as long as p is the smallest possible value for which this is true for all time, okay, so one could choose 4 pi, and this will also be true for all t, or 8 pi, but choose the smallest such p. It's still positive, not 0. Then that's called the period p. Period of this periodic function. Okay, so the possible periods would be 2 pi, 4 pi, any multiple of 2 pi will do. 6 pi, shouldn't be negative, just positive. And you just choose this one, and that's the period, what we will call the period of this function. You always try to choose the smallest of these shifts, which will make the graph repeat itself. All right. So for the sine function, for the cosine function here, the period is 2 pi. Okay, what is it for the sine function? And what does the sine function look like? Well, the sine function will be the plot of y of t. We'll see by graphing y of t versus t. Okay, so here's pi over 2 again, pi, 3 pi over 2, and 2 pi. And we'll go the other way, minus pi over 2, minus pi, minus 3 pi over 2, minus 2 pi. And 1 is here, minus 1 is here. Okay, so now this function starts off at 0, because we're looking at the y-coordinate now. When the t is 0, the point starts here. And when t increases, the y value, the y parameter or coordinate also increases. And so that will be an increasing function from 0. And then it will reach the value 1, the y component will be 1 when the point goes through the y-axis. So it will look something like this. And then we'll go down to 0 again when the point goes all the way to this point here along the negative real axis, next to negative x-axis, sorry. And then we go down here, and the y value will become minus 1 when it reaches this point, and 0 back again at 2 pi. And this will repeat, okay, forever. In the positive as t goes to infinity, and likewise in the negative x direction, this will repeat. This pattern will repeat in the same way. Okay, so if we draw, so these peaks here will be at, or valleys or troughs, the lowest points will be at minus 1, and the highest points will be at 1. Okay, so and there should be arrows here indicating this goes on forever here. And here. sorry. It's minus 2 pi there. It's over 2. Okay. Now, so again, you can see the period is 2 pi. Because I need that much to go back to a spot which is going to be identical in shape. The value of y will be the same, and also its shape of that curve at that point will be the same if I shift everything over here. Here I just can't go to here. It's the same value, but see, the slope here is increasing, and here the slope is decreasing. Slope is positive here, the slope is negative here. The instantaneous slope. So here I'm going up the hill, here I'm going down the hill. I have to go all the way over here before I go up the hill again. Okay, so this is a y. Y is a function of t. All right. So we sometimes call these functions are useful in physics. They are called the sine and cosine waves. Sometimes simply a sine wave. And you might guess that this function is the same as this function. That you just have to shift this one over, and that's actually true. So you can get from the cosine function to the sine function just by shifting the sine function over by to the right by pi over 2. So that means you'll add pi over 2. So right away you can check this equation. So adding pi over 2 will shift the sine function over, and then that will give you the cosine function. So this would be an identity that would come out of some of the identities that we'll see. One identity we've already given is the cosine of t is the sine of pi over 2 minus t. Okay, so another one, the one actually which will give this whole thing to us is if you change the sine of t, then this is sine of pi over 2. This is true for all t. So particularly we just change the sine of t, and that will still be true, except this will be cosine of minus t. I should put that in brackets. And now the cosine of minus t, this graph, okay, we'll see that this graph is even, which will make this function equal to cosine of t. So remember, an even function is one such that f of t is equal to f of minus t for all values of t. Okay, so it's reflection symmetric if you reflect in the y-axis. How can we tell this is reflection symmetric? Okay, so you look back at the original graph. If you go in this direction, the x-coordinate will start at 1 and go less. But if you go in the reflected angle, which is going to be minus t, the x-coordinate does not change at all. All right? So that if you reflect in about the x-axis here, then x of t will be equal to x of minus t. And so that tells us that this is an even function. However, for the sine function, so this is even. The sine function we can check is odd, because here as you go up in this direction, the y-coordinate becomes positive, but if you go in this direction, the y-coordinate has the same value, but it's simply changed sign. So in this case, y of minus t is equal to minus y of t. Here, x of t is equal to x of minus t without the extra minus sign. There's just one minus sign here. Here there are two. Okay, they don't cancel in any way. It's just telling you this is true for all t, then this is an odd function. Okay? So it can be shown to be odd directly from the original definition of the sine function, as well as this can be shown to be even just from the original definition of the cosine function, from the unit circle. All right, so good. So we've discussed then the definition of the sine and the cosine functions from the unit circle, which will make them well-defined for all values of t, positive and negative real numbers. So that means the domain, you can write down the domain is the real numbers here. And the range, well, these are all values from -1 to +1. So you can see the y values are restricted between those two values. And the same goes for the sine function. Its domain is all reals, and the range is from -1 to +1 included. Okay, so and with these identities, this formula is shown to be true now. So this is indeed a shifted version of the sine function is a shifted version of the cosine, and vice versa. You can think of the cosine function as a shifted version of the sine. There was another detail that I wanted to inform you of a little bit more, to talk about, and that had to do with calculating using the reference angle. So you want to calculate the sine and cosine of angles using the reference angle. All right, so this is what we need to use when the angle is outside of the first quadrant. Okay, so using the reference angle makes it a bit easier to think about when you calculate the sine and cosine of angles. So suppose you have an angle, say, out here like this. Let's say this is the angle 5 pi over 6. This is 5 pi over 6, so we're measuring the angle in radians. And this point is x, y. This is the unit circle, so this is radius 1, so usual points are here. 1, 0, 0, 1. So the question is, what are the values of x and y here? In other words, what are the cosine and sine of 5 pi over 6? All right, so now the way to do this using a reference angle is you complete a right angle triangle over here on under this point by dropping a perpendicular, or maybe lifting a perpendicular to the x-axis. So that's a perpendicular line to the x-axis, so that's a right angle. And now you have the reference angle is what? So remember how we define the reference angle. It's the smallest positive angle, acute positive angle, which this line, the final terminal line, makes with the horizontal axis, the horizontal x-axis. So we see there that its full angle will be pi minus 5 pi over 2. 5 pi over 6 is simply pi over 6. So that's the reference angle. So let's call it something alpha, let's say. Alpha is the reference angle. right? So it's always positive. It's between 0 and pi over 2, usually, always. So now we're assuming it's strictly between 0 and pi over 2. Okay, so now the principle is that the cosine and sine are the same in absolute value. Cosine and sine of the angle, this was t. The full angle the absolute values of those cosines and sines are the same, exactly the same as the cosine and sine of the reference angle. So let's just repeat that. So cosine of t is the same as the cosine of the reference angle when you take the absolute values of the cosine of t. And the sine of t absolute value is the same as the sine of the reference angle alpha. Okay, it's because if you compare this to the reflected triangle, if you reflect this, then x will change back to a positive value, y will stay the same. So both x and y will be positive. And then you can find, and the ratios, well, the x value will be the same as this, in absolute value as this x value. So you just take the absolute value of this and you get this. And the y values will be just the same because they're both positive. Okay, and the y value is the sine function. This is for, the y value here is the sine of the angle t. Right? And over here, it's the sine of the angle alpha. Okay, so wherever the reference triangle happens to be, whether it's that's in the second quadrant, so that's an example for the second quadrant. Here, the third quadrant looks like, now you have to, okay, here's the reference triangle. So the reference angle is right in here. So this one you have to rotate or reflect twice. You have to reflect in the x-axis and then the y-axis, and then you get this triangle here. So that would change. Here this changes to minus xy. This goes to minus x minus y. So since x and y are both negative here, that will change back to x and y, which are both positive. Minus x and minus y are both positive. And if I'm in the fourth quadrant, then the reflection is just through the x-axis. So here, x and y, here's the reference triangle, and I just flip it over the x-axis. And so I get x minus y. And so the negative y value becomes a positive y value. And it keeps the absolute values of these cosine and sine functions the same when you do this. So once you find the reference angle, you don't have to perform these. You don't have to picture all these manipulations, but you can simply write down the absolute value of the function and look for the correct sign. That's spelled SIGN. The sign of the answer will be positive or negative, and that you can find simply by looking at what the corresponding x or y value sign is, what the actual, whether it's positive or negative x coordinate in the case of the cosine function, or whether the y coordinate for the case of the sine function, whether the y coordinate is positive or negative. You would use those values for the sign SIGN of the final result. Okay, so let's see some examples here. Okay, in this example here, t is 5 pi over 6. My reference angle alpha is pi over 6. So the sine of t is the same as the sine of alpha with any extra positive or negative sign? No. It's just the same because the y doesn't change. So it's equal to 1/2. And then the cosine of t is now that's going to change sign. So I need a negative cosine of alpha. So it's minus root 3 over 2. So the coordinate of this point here, then, coordinates of this point are minus root 3 over 2 for x, and plus 1/2 for y. Okay, so you could verify that this is 1, 2, 3, 4, 5, 1/12 of the way around, and it should be a little bit higher in the x coordinate in its absolute value than the y coordinate, and that looks to be the case. So it should be the angle. It's closer to the x-axis than it is to the y-axis here. This value will be greater in absolute value than this one. Okay, so there's a simple mnemonic, which is like a memory tool for this, for finding the correct signs, SIGNs, of the final answers for sine and cosine. Sine and cosine spelled this way. Those would be, that mnemonic is, let's spell that out first. Oh, I don't even know how to spell it. Okay, I'm not sure how to spell it myself. So, okay, so, all right, now let's go just show you the whole thing. So it's A is for all, C is for cosine, T is for tangent, and S is for sine. And so this they suggest the mnemonic smart trig class in the book, or another one is just ACTS. It spells acts. You can think of other ones, but this is the order it should go. So this means all are positive. Sine, cosine, and tangent. That's what these refer to: sine, tangent, and cosine. Here, the cosine values are positive, and the rest are negative. The tangent will be negative, the sine will be negative. Here the tangent is the only one that's positive, the sine and the cosine are negative. Yeah, so the first quadrant, we can always write it all out. The sine is positive, the cosine is positive, the tangent is positive. The second quadrant will be the sine is positive, the cosine is negative, tan is negative. Here the tan is positive, the sine and the cosine are negative. And here the cosine is positive, tan is negative, sine is negative. Okay, well, so an even easier way possibly is you have the point here, you find the reference angle, you find the absolute values of the sine and cosine. It's just the sine and cosine of the reference angle. And then if it's the sine function, you choose the sine of the sine function to be positive or negative depending on the y value. The y coordinate here of this point is positive or negative. Here it will be negative. So you choose this. That's t, and that's alpha in here. And if you're looking at the cosine function, then you choose it to be positive or negative depending on whether the sine of the x coordinate is positive or negative. And so again, you get negative cosine alpha. Okay, so if you're in this quadrant, then, and that corresponds to these two. If the tan is the only one that's positive, then you must have the other two are negative. So that's what I'm depending on there. If you're in here, then you would change the sign of this one. This one would become positive, and this would remain negative. And if you're in this quadrant, this is the one that is going to change to positive, and this will remain negative. I'm sorry, this will change to positive, this will remain negative if you're in the second quadrant. Okay? All right, because remember alpha is a reference angle, so these values by themselves, sine and cosine, are both positive. Let's write that out. Sine of t is sine of alpha, and the cosine of t is minus cosine of alpha in quadrant 2. And sine of t is minus sine of alpha, cosine t is plus cosine alpha in quadrant 3. This should be 2, sorry. 4, sorry. Okay, so that's quadrant 4. So that's where you have minus and plus. And of course quadrant 1 has both. Both signs are plus. All right. Now let's see some other interesting facts here. If we take the ratio of sine to cosine, then that's gonna be the tangent function. Now, is the tangent going to be even or odd, or what is it going to be? Well, if we plug in minus t here, then that becomes a minus t in the sine function and also in the cosine function. And the top one is odd, so that becomes a minus sine of t. The denominator is even, so that's be plus cosine t. So the overall result is minus tan t. Okay, so this becomes this. We have two minus signs, one inside in the argument and one outside. So that means this function is odd. Tangent of t is odd. And similarly, you can do this for the other functions. If you take 1 over tangent of t, then that's the cotangent function. That's also odd. And if you take 1 over the sine of t, that's odd as well. So there are 4 functions. 4 of the 6 are odd, and the other 2 are even, namely cosine of t and the secant of t, the reciprocal of the cosine. Okay. So I'll write that down. The sine of t is odd, the cosecant of t is odd, tan of t is odd, and the cotangent of t are odd. And the even functions are cosine of t and secant of t. All right, so another note I want to tell you about is we had this identity before. The sine squared of t plus the cosine squared of t is equal to 1, and that's true for all t. Now we can get alternative, this is called the Pythagoras identity, or Pythagorean identity, because it's based on the Pythagorean theorem. Now there are other identities which you can get simply by dividing both sides of this one by some quantity. So we'll first divide it by the cosine squared of t. So divide both sides of the equation by cosine squared of t, and we'll get each term gets divided now by cosine squared t. So this becomes sine squared t over cosine squared t. This becomes simply 1, and dividing cosine squared by itself. And then on the other side we got 1 divided by cosine squared of t. So this function here you can see is this tan squared of t. The 1 is just the same one, and then secant squared of t. So this also is true for all t. And then by dividing by sine squared t, starting from the original one, you can get a further identity, namely 1 plus cotangent squared t is equal to cosecant squared of t. So that's also true for all t. So these three identities come from one another. So it's sufficient to remember this one, to recall or memorize this one. And then this one will easily follow from this process of dividing by cosine squared of t. And then the second one will follow from this by dividing by sine squared of t. All right, so let's try using our knowledge of the trig formulas and identities to simplify things. So this is similar to what was given in the textbook as the last example in this chapter. So it's simplify cosecant t divided by cotangent of t. So the first numerator is 1 over sine of t, and the denominator is cotangent of t. That's defined. So the easiest way here is to express all the functions in terms of the two basic ones, sine of t and cosine of t. And so you'll get cosine of t over sine of t here, because the cotangent of t is the reciprocal of the tangent of t. Yeah, so this will be 1 over the sine of t times, and put this in the numerator, so we have to interchange numerator and denominator there, and then you cancel the sine of t. And so you'll get secant of t. So that's all it is. That's all this turns out to be, is just the secant function of t. All right. There's a space there, so that's not, it's a secant, and then I've just not included the brackets instead, and it makes it a little bit more easy to write down. Okay, so let's use the Pythagorean identity. Suppose you have an example. Here's an example problem. So you are given sine t is equal to this number, 4 over 5. And you're told that the angle t is in quadrant 2. Find cosine of t. Well, first of all, is that true? Can this be in quadrant 2? And the answer is yes, because in quadrant 2 the y value is positive. So positive value is allowed for the sine of t. But the cosine of t, if this is quadrant 2, must be negative. Okay, so we can solve for cosine of t by using the first Pythagorean identity. So we write cosine on one side and solve for it. Cosine squared goes on one side, and you get 1 minus sine squared on the other side. You just plug in the numbers here. So it's 1 minus, this will be 16 over 25. 1 minus that will be 9 over 25, which is 3 over 5 squared. So cosine of t is plus or minus 3 over 5. Now we want the negative value because we're in quadrant 2. So we just reject the positive one, and that's our answer. Okay, so let's try a slightly different one. So if you try some different problems, you can always make up your own problems and try them out, see how it goes, see how far you can get. So here, if the sine of t is 2/3, and t is in quadrant 2 again, then this calculation will give you, what will give you in the end? Well, you'll see that it gives us minus, and I'll get square root of 1 minus 4 over 9, which will give me, this will be 5 over 9, square root. It's a positive square root here now. So that will be minus root 5 over 3. Okay, so you can see it won't always turn out to be nice. This is nice because it's a 3, 4, 5 triangle that underlies this, that this angle forms with the vertical line and a horizontal line. But this is not such a triangle. It's not a so-called rational triangle. It's just a regular, just some other triangle. So you get a square root in there, and that's true in general. All right. Okay, so now I wanted to do more problems in the final section, so let me just work on that. So we go to the, I'm going to the practice test at the end of chapter 7 here. So the first problem is convert 5 pi over 6 radians to degrees. This is a chapter 7 practice test. Okay, I'll do the even ones because the odd ones have answers in the back, and so you could at least try those and see how you do. If you have any problems with them, please let me know. I could try to help you by chat or Skype or something. So convert 5. So the first one I guess I'll do anyway. Number 1 is convert 5 pi over 6 radians to degrees. So 5 pi over 6 radians. So we just multiply by 180 over pi. Cancel the pi's. The 6 will cancel with this, giving me 30. 30 times 5 is 150. So that's my answer. 150 degrees. Number 2, convert minus 620 degrees to radians. So now minus 620, now I multiply by the reciprocal of that conversion factor. That should be degrees. Okay, so here the units, degrees will cancel, and so will 10. And this is 18, this is 62. The 2 will cancel here and give me 9. 2 will give me 31. So this could be written as a fraction, 31 pi over 9 radians. Okay, so that's really not too hard, hopefully. Find the length of a circle. So you just use a conversion factor here. So the answer, if it's negative, stays negative. If it's positive, it stays positive. Okay, the number 3 I'll let you try. Number 4, find the area of the sector with radius of 8 feet and an angle of 5 pi over 4 radians. Okay, so the angle is 5 pi over 4 radians. The radius is 8 feet. Remember, no units means that it's an angle in radians. Okay, so we use our formula half r squared alpha for the area of a sector. The sector will look like this. So that's the area of this sector. And this is 8 feet. So I just plug in the numbers and I get 1 over 2, 8 feet squared, and 5 pi over 4. So that's 64 times 5 pi over 8. So I get 8 times 5 is 40 pi. And the units are square feet. And 40 pi is about 120, it looks like. To be more exact, that's 125 or 125.7. Or 0.66, let's say, square feet. Okay, find the angle now, number 6. Find the angle between 0 and 2 pi. Find the angle between 0 and 2 pi in radians that is coterminal with minus 4 pi over 7. Okay, say that again. Find the angle between 0 and 2 pi in radians that is coterminal with minus 4 pi over 7. So we want to find alpha. Let's call this t. Okay, so it's not, let's see, it's not quite the same as the coterminal angle, so let's use a different number. It's not the same as a reference angle, that's what I'm trying to say. So coterminal means that it's anywhere between 0 and 2 pi, as opposed to outside that range. Okay, so we just want to add whatever multiple of 2 pi we need to just get over 0 here and not go any more, not go any higher, and that should put us in the correct range. Okay, so if we add 2 pi, then we can see right away we get a positive number because 2 is bigger than 4 over 7. So that's all we do, add 2 pi. And we get 2 pi, the result is beta is 2 pi minus 4 pi over 7, which is 2 minus 4 over 7 pi. That's going to be 14 minus 4 over 7 pi, or 10 over 7 pi. Okay, now we do it again with draw the angle minus pi over 6 in standard position on the Cartesian plane. Okay, so here we have to draw a graph, or draw the picture. Minus pi over 6 is going to be somewhere down here. So that's the standard position where you have the starting side is on the x-axis, and the terminal side is obtained by a clockwise rotation because t is negative here. Okay, so that's about 30 degrees. So that's the standard position. That's number 8. Number 10. Find the missing sides of triangle ABC. Sine B is equal to 3 over 4 C is equal to 12. Okay, let's try drawing it this way. For starting out, let's see how this works. So sine of B, so here they're just using the actual vertex as the label of the angle. So that's the same as beta. So the sine of B will be, using the small letters for the sides, B over C. And C is equal to 12. Okay, and we're given that sine of B is equal to 3 over 4. Okay, so C is 12. What are the remaining sides? So we're assuming C is the right angle here. Capital C is the right angle. And A will be, if we knew B, then A is just the complement of B. In radians, A plus B is pi over 2, or 90 degrees in degree measurements. Okay, so let's see. So first we're given the value of C, and if we knew B, then we could get all the sides. Well, we can get A by Pythagoras. Well, that's just found by, B is found just by solving this ratio. We know C, so we know B over 12 is equal to 3 over 4, or B is equal to 12 times 3 over 4. 4 is canceling at 3, so B is 9. So what does it look like? It's 12 here, 9, and what is A? So A squared, using Pythagoras' theorem, A squared plus B squared is C squared, so A squared plus 9 squared is equal to 12 squared, which is 144 here. A squared is then equal to 144 minus 81, and that's equal to 63. So A is equal to square root of 63, which 63 factors into 9 times 7. So take the 9 out and then leave the 7 in. So that's 3 root 7. Okay, so that's what A should be. All right. So those are the missing sides. Of the triangle. Okay, so I'm just skipping the odd ones because I want you to, the answers are in the back of the book, so you could try working on those yourself. So here now I do number 12. The angle of deviation to the top of a building in Chicago is found to be 9 degrees from the ground at a distance of 2,000 feet from the base of the building. Use this information to find the height of the building. So I'm just going to show you how it works. So we're starting here, we're looking on the ground, we're close to the ground here. The building's a tall thing, it's far away, and we're seeing it at an angle above the horizontal, and that angle is 9 degrees. So we're given 9 degrees from the bottom to the top of the building. And we're also told that the distance along the ground to the building is 2,000 feet. So we'll call this side, this length A, that's 2,000 feet. So what do we want to find? We want to find the height of the building, B. All right. So we could use trigonometry here but we'll need a calculator. How do we use trigonometry? Well, we're given this angle 9 degrees. That's going to be our beta. Now C, we don't know that either. If we don't know B, then we can't use Pythagoras to calculate C. But we'll just leave that alone for now, and we'll see what function, what trigonometric function will, if we knew that value, will enable us to find B in terms of C. Okay, so if you think about it, we'll just need these two sides, and those two sides in ratio form give us the tangent function. So if we knew the tangent function, then because we know A, we could also find B. What is B in terms of this tangent function in A? It's just A tan beta. Okay, so let's put in the values now. Tan 9 degrees. And now we'll use a calculator. So now because this is 9 degrees, I have to not just put it into my calculator, I have to change my mode first. So I go 1, 2, 3 like I did before, and I type in 1, which will give me degrees. And then I type in, just to find out what the tan is by itself, tangent of 9 degrees is, I'll take tangent of 9, and that's by itself 0.15838, and so on. Or you could do it by the sine of 9 degrees divided by the cosine of 9 degrees. But we have the tangent function on the calculator, I might as well use that and do it all in one step. And we just multiply that by 2,000. And we get 316.8 feet. Okay, so that's how high the building is. And that finishes our problem. Now we should look at the specifics here. Should we round it off, or it doesn't say anything about that, so we'll just leave it in this form. If you wanted to round off to the nearest foot, then it would be 317. All right. Now the next one, we have 5 more to go here. Number 14, compute the sine of 240 degrees. I'll just leave this on for a moment. Compute the sine of 240 degrees. All right, so we'll do this using reference angles. So 240 is between 0 and 360. It's going to be in the third quadrant, because the third quadrant is all the angles from 180 degrees to 270. Okay, so how far along is that? Well, it's going to be all the way up to here, I believe, because this is 30 degrees difference, and this is 60 degrees. So the reference angle then will be 60 degrees. So this will be the same as the sine of 60 degrees. But we just need to figure out whether it's positive or negative. And the answer is because both y and x are negative in this quadrant, or the third quadrant, we should have a minus sign there. And then we just need to write out the answer for 60 degrees, for the sine of 60 degrees, that's minus root 3 over 2. Okay, so you see the steps there. You locate the quadrant in which the angle sits. You find the reference angle by finding the smallest positive acute angle between that side and the horizontal axis. Then you write this either sine or cosine or whatever of the reference angle instead, and determine the sign in front, the positive or minus sign, by checking which quadrant it's in. And remembering whether y coordinates or x coordinates should be positive or negative there in that quadrant. and that will determine the x, whether it's plus or minus for the x-coordinate determines the cosine, and whether it's plus or minus for the y-coordinate determines the sign of the sine function. Let's do number 16. State the range of the sine and cosine functions. And we saw before that the ranges are both -1 and 1. So you only change between the real numbers between -1 and 1 inclusive, and you can obtain any value as long as you adjust your angle accordingly. Okay. So remember, it looks like this. For the cosine, for example, +1 and -1. One might ask also, are these functions one-to-one? The answer is no, because if we draw horizontal lines, we fail the horizontal line test for a one-to-one function. It will intersect in infinitely many places there. So it's not one-to-one, but we'll see later we can restrict the sine and cosine functions so that in ranges, in intervals which are now the new domains, and in those new domains the functions will be one-to-one. So we will be able to take inverses of those functions. I'll do that next time. Use reference angles to, this is number 18, sorry. Find the exact value of tan pi over 3. So exact value means write it in using square roots or rational numbers. And don't use a calculator to round it off. Okay, so this we recall is the same as sine of pi over 3 over the cosine of pi over 3, and using a 60-90 triangle, this comes from the 60, that's 60 degrees, or pi over 3, 30, 90 degree triangle. Okay, so remember this side, if this is side length 2, then the shorter side, this hypotenuse is 2, the shorter side then is 1, and the in-between side is √3. So that's what it looks like. Angle pi over 3 is bigger than pi over 6. So the sine of this angle is √3 over 2. And the cosine is 1 over 2. So we'll see that the 2's cancel and I get √3 only. Number 20, use reference angles to evaluate tan of 210 degrees. Right, so its reference angle is 30 degrees. Okay, so now I evaluate by, well, I can do the same thing as I did for sine and cosine. I replace this angle by the reference angle, and it's just 30 degrees, and simply determine the sine based on what I know about this angle and its functions in that quadrant. And I recall that the tan is positive in this one. That's the third quadrant. So this remains positive. And I recall also the tan of 30 degrees is the sine of 30 over the cosine of 30. And that's sine of pi over 6 over cosine of pi over 6. So I'll just get 1 over √3. So some of this I can do from memory. Some, if I forget some of it, I can just check it by calculating, for example, sine of 30 cosine of 30. Sine of 30 is easy to remember. It's 1/2. And this is root 3 over 2. You take 1 minus the square of 1 over 2, and then take the square root of that, and I get root 3 over 2. So again, I get the same, which checks. Okay, always try to check your answer in some way, so it's good to learn 2 or more ways of doing the same problem, solving the same problem, so you can always check using an alternative way. If it's right both ways, then that helps you be quite assured, much more assured that you're doing it the right way in the first place. You're getting the right answer. If one of the ways is wrong, then you should check a third way possibly to see where the mistake might be. Okay. Now, number 14, where are we at? Number 22, the final one in this section. If cosine of t is root 3 over 2, find cosine of t minus 2 pi. So cosine of t is root 3 over 2. Find cosine of t minus 2 pi. And okay, this one is pretty easy. Since cosine of t is a periodic function, I was just explaining that. If we add or subtract multiples of 2 pi to this, it doesn't change the function, so we can go right back to the original function. So this is just equal to this value of root 3 over 2, and that's all we need to do. Okay, so I finished this section a little bit over time this time. So I plan to now continue. We've already gone into chapter 8 by doing the graphs of the sine and cosine functions. So I'll continue with the graph of the tangent function next time, as well as the reciprocal functions to the tan, namely the cotangent function, and also reciprocals to the sine cosine, namely cosecant and the secant functions. I will also attempt to discuss the inverse trigonometric functions, as well as more identities, possibly involving the sine and cosine and tangent functions. And so that we should soon be able to wrap up the chapters on trig functions. Okay, so have a good day, have a good night as well. Take care.